Bond enthalpy calculations is one of the higher-only topics within Unit 5 of AQA GCSE Combined Science or Chemistry. These calculations are actually really straightforward, but they're a little bit intimidating at first glance, and so sometimes people leave them out. That means if you can give them your best shot, you're putting yourself at a big advantage. So to start with, we should just remind ourselves of some basic energy facts. Firstly, energy is conserved in chemical reactions. That means that just like we can't make or destroy atoms, we can't make or destroy energy. There has to be the same amount of energy in the world at the start and the end of a chemical reaction, but it can move around between different chemicals in the reaction or between the reaction and its surroundings. Every chemical reaction absorbs and releases energy. So to classify reactions, we think about what they do more of. Overall, an exothermic reaction heats up the surroundings because it gives out, or emits, more energy than it absorbs. Likewise, an endothermic reaction cools down its surroundings because it's absorbing more energy than it's releasing. The reason these reactions absorb and release energy is all to do with bonds being made and broken. To break a bond requires energy to be absorbed. Imagine two atoms stuck together with glue, and to break them apart you have to put in a load of effort. Then, when you make a new bond, you're doing the opposite, so that must release energy. We can see this in an energy profile diagram. The reactants have a certain amount of energy. In the first stage of the reaction, they absorb more energy from the surroundings, so they have more than they did before. This is when the bonds are breaking. Then, after the bonds have been broken, energy is released as the new bonds are made. If, like on the left, there's more energy released than there is absorbed, then we call this an exothermic reaction. If, like on the right, more energy is absorbed than is then released, the reaction is endothermic. So that's all lovely, but sometimes we don't just want to say, oh, this reaction's exothermic, this reaction's endothermic. We want to actually put a number on it, how much energy is going to be released. This can be important for figuring out whether a reaction is feasible, so whether it will actually happen in real life or it's just theoretically possible, or also just for figuring out whether something is exothermic or endothermic. If you're going to do a reaction at 600 degrees to make it go faster, you can't exactly just stick a thermometer in there to figure it out. But whether a reaction is exothermic or endothermic is really important if it's reversible and you're wanting to think about yield. So anyway, that's why we want to do these calculations. Now let's actually think about how we would do them. So the first thing you need to know is that for every different type of bond, there is a different number for how much energy it would take to break that bond. And you can look these up in a data table like this. Now for your GCSE chemistry exams, they're going to be nice to you. They're only going to give you the bonds that you need. So what this table tells me is that if I had a mole of carbon-carbon single covalent bonds, it would take me 347 kilojoules of energy to break all of those bonds. And if I had a mole of carbon-carbon double covalent bonds, that would take me 602 kilojoules of energy. So you don't really need to worry about the numbers. You're not expected to memorise these. You just need to appreciate that for every different type of bond, there's going to be a different amount of energy required to break it or released when it is made. So a typical question might ask you to look at a reaction like this and work out what the overall energy change is, what we call delta H. Now firstly, a little bit of exam technique. When the exam board set a question like this, they're going to give you a balanced simple equation, and they're also going to draw the molecules underneath, because you need to know what the molecule looks like. It's not enough to know what atoms are in the compound, you need to know what's actually directly bonded to what. So that's quite nice and charitable of them, but when they do this, they'll only ever draw one of each molecule. And as you'll see, one of the biggest problems that people have with these questions is that they end up forgetting that they've got two hydrogen molecules or two water molecules. So I would strongly suggest that you take all of 10 seconds to redraw any molecule that is in that equation more than once. So here, I've got my hydrogen molecule and I've got my water molecule, but the first thing I'm going to do is draw another one of each. So now that I've got the right number of molecules, the first thing I want to be thinking is which bonds need to be broken. So I've got my two hydrogen molecules, each with a single bond in them, and they need breaking. And then I've also got my oxygen molecule, and that contains a double covalent bond which also needs breaking. And I should probably also point out that if you're given the value for a double bond, that is the amount of energy to break the whole double bond. Sometimes you'll see people going, oh, it's a double bond, I need to put it in there twice, but that's not something you need to do. Now I've picked really simple, straightforward molecules for this example, but sometimes you're going to get more complicated molecules. And what we always see is people forgetting about some of the bonds, or only breaking some of the bonds, or miscounting. So what I would always recommend you do is physically cross out each bond in turn, and as you do, write down the value for that bond. So even though I could just go, oh, hydrogen's worth 436, I'll do 2 times 436, what I would personally always do is cross out the first one and write 436, and then cross out the second one and write 436 again. I know this sounds really patronising, but when you get a more complicated molecule, it's going to stop you from making silly mistakes. So I've crossed out my 3 bonds and I've written down 436 for hydrogen, hydrogen, 436 for hydrogen, hydrogen, and 498 for oxygen, oxygen double bond. And if I add all those up, I can see that this reaction is going to need to take in 1,370 kilojoules of energy. So next I need to think about making some bonds. I'm going to make 2 water molecules, so I'm actually going to need to make 4 oxygen-hydrogen bonds, and each of those has a value of 464. So again, I'm going to cross out each bond in turn, or colour them in with a green highlighter, and write down 464, 464, 464, 464, and if I add all of those up, I get 1,856. So then the last step is really straightforward. It's just looking at what is the difference between these 2 numbers. And unusually for chemistry, I don't have to do anything funny with switching numbers over. I'm literally just going to put a minus sign between my 2 numbers. So I'm doing the energy taken in minus the energy released. And that gives me a value of minus 486, which is what we call the delta H, or the overall energy change. Now, in terms of what that means, it means that my products have 486 kilojoules of energy less than my reactants did, assuming that this is all happening for 1 mole. So if my products have less energy than my reactants did, that's because the energy's gone somewhere, right? It hasn't just disappeared. We said at the start that energy has to be conserved. So if it's not in the product, it must have been given out to the surroundings. So this negative number here tells me that my reaction is exothermic. And if I had a positive number, that would tell me that the reaction was endothermic.